So next speaker is Huijing Gong, correct? Yeah, okay, I guess right, yes. And she'll be talking about security guidelines implementing homomorphic encryption.
Okay, thank you for the introduction. So I'm going to present our work on this security guideline. It is a collaborative work among 19 researchers from who joined independently and some other institutes, including Intel Labs, Zama, Royal Holloway, University of London, Lorca Cyber Security, and TikTok, etc. Yeah. Yes. Oh, sure. So one of the challenges of widely adapting the FHE into practice is parameter selection, which involves the multidimensional trade-off among security, functional correctness, and efficiency. So there can be a very easy misuse to set up some things to achieve very great performance will sacrifice the security, right? That's definitely what we don't want. So our first goal is to bridge the gap in security awareness among HE experts, engineers, and end users. There are also great prior work to do to this by homomorphic.org organization, and that work was released on 2018. So our document is to update and expand the parameters based on their work. So the third goal for us is to supporting the ongoing standardization process on FHE by ISO and IEC organization. So at the very beginning, our project was initiated as a part of the ISO standardization, but later we split it out because we think it will allow us to update the parameters more easily. And yeah, so the targeted schemes of our work still aligns with the ISO IEC standards, which is BGV, BFV, CKKS, and the CGGI. Okay. Oh. Okay. Let's take a closer look of the comparison between our work and the prior work. So our work provides broader options of dimensions and distributions. Specifically, we have the distributions. We have the secret distributions that include Gaussian distribution, ternary distribution, and binary distribution, where the binary distribution is not included in the prior work. And we also provide the broadened range of the standard deviation of the error distributions. Whereas in the prior work, it's they have the fixed standard deviation, and for the dimension, our dimension is go up to the power of 17, and where in prior work is to the power of 15, and of course we updated the parameters with the recent advancement in the cryptanalysis, and also provided open source tools based on the latest estimator for individual to update the parameters, which the prior work does not provide the tools. Yeah, so for another part of the scheme of our document is we provide the scheme parameter examples for BGV, BFV, CKKS, and the CGGI. Yeah, and that includes the parameters that are relevant to the security and also the parameters that are relevant to the functionalities. Additionally, for the other contents, in contrast with the prior work, which provided details on the FHE constructions and the details on the attacks, we only provide the references. And the additional brief discussion that I just want to mention here, we also have the very short discussion on the entry-based FHE, machine learning attacks, side channel attacks, and a relatively new security notion, indistinguishable CPAD. Okay, so let me go over the outline of our work and also the talk. So the first, we kind of discussed the methodology for doing this security analysis with focus on the security notion and assumption, the harness assumption. And then we defined the security levels that we targeted. And then the security tool, the two estimation tool that we used for the analysis. And after going over the methodology, we are going to talk about the parameters. So the first is it's about the security, which is the parameters from the underlying LWE instance that with the targeted security levels. And then we show the scheme parameters as examples. Lastly, we provide the parameter selection. We provide a survey of the parameter selection across the open source FHE libraries and compilers. Okay, so the focus of our security analysis is we still focus on the indistinguishable chosen plaintext attack, and that would be based on the harness assumption of the decision learning with errors. And with its variance, ring learning with errors, and general learning with errors, which also known as the modular learning with errors. So for the concrete security, we focus on the parameters of the underlying LWE instances of the homomorphic encryption. And since the algebraic structure of those variants are not has not been exploited for the practical applications yet. So we just treat the RLWE and the GLWE as the LWE by doing some conversion. So next, I'm gonna briefly talk about those harness assumption. So for the learning with errors, it is parameterized by a dimension n, which defines the dimension of the vector S and the vector A. And the modulus Q, which is the modulus operations for this whole computations. And the chi of S is the secret distributions to sample the secret vectors. And the chi of E is the error distributions to sample the error. So the decision LWE problem is to say that there is the indistinguishable computational indistinguishability between the LWE pair, which is defined on the left-hand side, and the random pair. Okay. So, and for the GLWE, we can just view as replacing the each entry from ZQ to RQ, where RQ is like a polynomial ring with dimension big N and modulus Q. And here was to note that the dimension will be denoted as K. So when we do the and when the K equals to 1, it is the ring learning with errors. And when we do the conversion to the learning with errors, and the K multiplied with the big N will becomes the dimension small n of the learning with errors. Okay. Okay. So next, we will delve into the error discussion on the error distributions. So for the harness assumption, it's saying that if the standard deviation of the error distribution is omega of square root of n, then the best known algorithm to attack this LWE problem requires exponential time. But however, in the practice, for both FHE domain and the PQC domain, we have much narrower choice for distributions. So, so one common way for the power of 2 cyclotomics, we let Gaussian distributions to have the standard deviation becomes to 3.2 or 3.19. And it is also equivalent to say that for non-power of 2 cyclotomics, we just need to multiply by a factor of square of k, and where k is the k cyclotomic rings. There are also an alternative distribution, which is centered binomial distributions, which can provide the constant time sampling. And so our work is focusing on the Gaussian distribution in power of 2 cyclotomics. Okay. And then let's move to the sacred distribution. So for the hardness assumption, it's defined using the either the uniform sacred coefficient that are uniformly sampled from ZQ, or the normal form sacred, which follows the error distributions of the hardness assumption. But for also a similar case for the practical choice, the Gaussian distribution are chosen from a much narrower standard deviation. And also we have the ternary secret that are used pretty widely nowadays. And those are coefficients that are sampled uniformly from -1, 0, 1. And similarly, the binary secret are coefficients that are sampled uniformly from 0 and 1. There are also some sightings that coefficients are sampled from -1, 0, 1, but with the predefined number of non-zero coefficients. So if these numbers becomes very, very small, then we call it a sparse secret. So note that those distributions may account for different attacks and also may achieve for like a FHE efficiency. Okay. So after going over those and for our work, we are more focusing on the Gaussian secret, ternary secret, and the binary secret. Okay, great. So I'll just go over the kind of background, and this next is the security levels that we are interested in. So we follow the definition from the NIST PQC standardization on the quantum security levels with category 1, 3, 5, which is equivalency to the cost of quantum computers required to break the EAS with the corresponding K-sets. And correspondingly, we define the similarly for the classical security levels, which is used in the cost matrix of the classical computers. But in practice, we don't really do those kind of quantum gate counting or something. We use the lattice estimators and are choosing the cost models for like the PKZ subroutine as above. So we use the cost models of the BDGL as 16 as the classical setting, and the La-Mos-Paul 14 as the quantum setting. And for the cost matrix, we just follow the unit used in the lattice estimator, which is mirroring the workload in the ring of operations, and they can be converted into the CPU cycles in the classical computer setting. Okay. Next, I will talk about how we generate those security LWE sample tables. So we provide the LWE parameter sets that are more applicable for the BGV, BFV, CKKS, the CGGI, that targeting to these six levels. And also the parameters that we have right now are verified from the latest lattice estimator as of the February 27, 2024. And the set is actually validated against the K attacks, including primal unique SVP, primal BDD, primal hybrid, and primal dual. Okay. So for the security tables, we provide two tables. One table has the style that are more applicable to the BFV, BGV, and the CKKS. So you can see from the example that due to the space, I just take like a part of the table. So it has the fixed Gaussian error distributions, and for each n and the sacred distributions, we calculate the maximum possible log Q to achieve the targeted security levels. and the dimension n is from 1024 to up to 2 to the power of 17. And for the secret distribution, we use the ternary and Gaussian distributions. And all the 6 security levels are included for this table. And for another table, for the second table, it is more towards the CGGI applications. So instead here we have the fixed log cube, which is to be 32-bit or 64-bit. And for each dimension n and security distributions, we calculate the minimum log sigma, which is the standard deviation of the error distribution, that to achieve the targeted security level. So here, n is not restricted to the power of 2 because n can be the LW instance. And the secret distributions here includes the ternary, binary, and Gaussian distributions. And also it includes all the 6 security levels. Okay. Okay, so you might wonder what if there's some like a recent cryptanalysis attack comes out and how that would impact our parameter tables. So we realized that it will be very challenging to do this kind of prediction. Previously we are thinking to get some security margin, for example, security margin K for the next X year, so we kind of generate the tables to target it to the security level, for example, 128 plus K. But it's quite challenging. It's quite challenging to do this, and there's no, it's hard to find some like Moore's law for this lattice cryptanalysis field. So instead, we provide the script. So it allows everyone to rerun, to update the parameters if the lattice estimator integrated those newest attacks. And it also provides the flexible adjustment. So user can modify the settings. For example, they can change the cost models or like have put some more focus on some specific attacks. Yeah. Okay, so next I will briefly talk about our scheme parameter set. Set example. Those are the set examples to meet some specific security targets, security levels, while achieving certain functionalities. For the BGV, BFV, we have the examples for the somewhat homomorphic encryption, like without bootstrapping, on a seal library. And for the CGGI, the parameter examples actually are provided by the TFEG-RS, TFEG lab, and OpenFEG. And for the CKKS, we provide 2 tables. One is for the case without bootstrapping, and that's based on the OpenFEG implementations. And the other one is with bootstrapping. That is based on the both OpenFEG implementation and Latigo implementation. So at the end, we provide a survey for parameter selection across various FEG libraries and compilers. So this survey actually highlights the critical need for a systematic approach to parameter selection across FEG libraries, because most of the libraries are kind of using a pretty simple or example ways to generate the parameters. Yeah. Okay. So at the end, I will talk about our collaboration. We started on September 2021, which was actually as a project for ISO IEC standards with the security focus. And later, our team grows to include 19 researchers from industry and academia, and people join independently. And we have the expertise in the lattice cryptanalysis and some major FEG libraries and with their variants. schemes and their variants. We also hold like regular meetings that integrate those expertise and fostering numerous consensus and solutions to get to this security guideline. So we believe that it will be very helpful for the growth of the FHE community, or also the growth of the FHE field, to have the efforts in bringing security awareness, or writing the security guideline, or even in the future providing the security assurance to be continuously evolving. Yeah. So okay. So the key takeaway of my talk is, for those implementing the HE schemes or our applications, so up-to-date security guideline is essential. And for our document, we provide the updated parameters in response to the recent cryptanalysis advancement, and also we provide the scheme parameter set examples, and also we have the open source tools to kind of let users can generate or update the parameters independently. So and also there are we also highlight two future directions. So one is to expand the scope to include more schemes like the entry-based FHE schemes, or have more diverse distributions, or and include a broader attack scenarios. So another one is, as I mentioned earlier, so that is to develop advanced automated framework for systematically choosing the parameter selection, pretty optimal way that can balance the security, functionality, and efficiency well. Okay. Thank you, and you can find our guidelines on the ePrint, and also we have the scripts available from these two GitHub links.
Thanks for the talk. I was wondering if you can expand on how you have constructed these tables.
Which table?
The tables that you presented. I don't remember the slide where you showed the perimeter, the security level, and this one. Yeah.
This one?
Yes.
I can talk about this. So for this one, for generating this one, we first kind of approximate using some I think a linear. That's pretty simple. We kind of predict, for example, given n, what is the corresponding log Q using a very rough, a linear regression thing to predict a rough number, and then using the boundary search to find the optimal points to achieve this goal. Yeah.
And you do this for every attack?
We kind of run the whole attack. Yeah, but I think there's also something to be we want to mention, for the hybrid BDD, it's pretty costly when the dimension goes very high. So there's ongoing efforts to improve the BDD subroutine, and also we have some experiment that shows that when the dimensions goes up, the advantage of the hybrid BDD compared with other attacks kind of goes pretty converges to zero. Yeah, but it's just from the experiment based on the dimensions below 16K. Mm-hmm.
Thank you.
Sure.
Thank you very much for the presentation and for the great work. It's really important for the ISO standardization. Mm-hmm. And I have a question about the future. Is this group plan also to consider some of the modules as in the CPA-D and to propose params for the exact FHE schemes that are compliant with this notion regarding the two new papers and the security vulnerabilities on it?
So we're asking if we are going to consider the CPA-D
exact proposed params that are compliant with NCPD for the exact feature schemes.
I think it's definitely important to consider it in the future. Just for this current draft, because it's kind of still evolving, and I think just a few like maybe around recent weeks there are some other papers on CPAD secure notion that are talking about the BGV, BGV, the exact FHE schemes are still can be vulnerable. And also this kind of things can highlight how important that we need to choose the parameters that ensures good negligible failure probability. So it can further ensure the security. Yeah, I think that's definitely important to be included, and we can call for like a contribution from the community.
Thank you very much. Yeah. That will be really useful. Thank you.
Mm-hmm.
Hi, thanks for the talk over here. I'm wondering about the results from your survey. Like largely speaking, were most of the compilers libraries using secure parameters, like say over 128 bits of security, or what were the findings?
Oh, so sorry, could you say again?
You did a survey of a bunch of libraries and compilers, right?
Mm.
What were kind of the high-level results? Were most of them secure, or what did you find?
We actually didn't focus on this. We are more focusing on the schemes of the parameter selection, like what kind of scheme they use to choose the parameters. Yeah.
Okay.
Yeah, maybe I can talk about for the OpenFG, which I'm a little bit familiar. So OpenFG they provide the security levels that you can do it for the setting, like when it could, but they also can kind of, it's not forced. You can kind of change it to like a non-set. So yeah.
Okay. Thank you.
Mm-hmm. Thanks.
Thank you for the presentation and for informing these developments. You mentioned that one of the goals of this work is to support the ISO standardization. Could you explain, does that mean that in practice you are working closely together and the authors are also invested in the ISO standardization process, or are those independent works?
That's a good question. Like we have some authors also like working in the ISO standardization, and to be noted that ours is not to like replace or like kind of placing the same rule of the standardizations. Like we didn't really standardize anything. We just provide security guideline. Whereas in the security standard, whereas in the ISO IEC standardization, they have like a more detailed discussion or standardization on the FHE constructions. Okay. So it's kind of different. Yeah. But
in practice, you're expecting that these guidelines you're developing will be useful for those standards in practice?
I think they will set. It will be set in the ISO IEC. Okay. Yeah.
Okay. Thank you. Could you also please show the IACR reference, because I couldn't IACR. Get it. You had it on your last slide, 2024/something. The ePrint version, the ePrint reference.
Let me see. Yeah.
Thank you.
Thanks. Yeah, sure.
Do you think the table of parameters might be, helpful if different tools, for example, OpenFHE, Seal, and other libraries, do you think it might be helpful if all of them might use similar parameter sets so that it might support interoperability between different libraries? Or, you mentioned like the user can, use their own, parameters if they choose to. Do you think it might be helpful to have like a standard set of parameters for different libraries, or, it's not that helpful?
I think it depends on like, I hope there's kind of maybe some compiler things or some efforts to do this kind of systematic optimizer for those parameter set. So, if, for example, if we're giving the parameters like the parameter examples, but maybe like some application actually use some, because the application we cannot provide examples for all the applications, right? Like exhaustively. So there's something that it's not optimal enough. So instead we provide upper bound, so people can kind of adjust themselves. Yeah. Mm-hmm.